Okay, so if everyone could pass around, if you could take one sticky of each and pass them around. We'll use these to say when you're done with an exercise and when you need help and that type of stuff. So we'll get all of those sent around. So we'll get started in a couple of minutes. I'm just going to ask a few questions. Who's been using Python for more than 2 years? Cool. Who's been using Python for more than 5 years? Who's been using Python for more than 10 years? Yeah. Who loves Python? Yes. Okay. What's that? Less than a year. Great. Anyone else less than a year? Fantastic. Yeah, appreciate that. Who's considers themselves somewhat proficient with the SciPy stack? I mean, like NumPy and Pandas and maybe scikit-learn, AstroPy. No, I'm kidding. I mean, some of you will be. I'm not. Yeah, I wasn't. Insulting astronomers like the second minute of the workshop. Which would be horrible. So we're getting the stickies passed around. Where are they at currently? Okay, great. Cool. Yeah, it's incredible, and I'd really, yeah, and I would encourage you to reach out to the Binder team as well and tell them how great you find it. And if you have any issues, raise issues on their repo, or pull requests are better. But yeah, it's very cool. I wouldn't suggest doing this now, but I just found out in Binder, if you see it ends with, tree, notebooks. If you change that to lab, it launches a Binder session of Jupyter Lab. We're not going to do that now for a reason that may become apparent downstream, but it involves IPy widgets. So we'll start in a minute. Eric, did you want to say anything to start, or?
Yes, actually. Okay, so just like with the network analysis tutorial that I was just in, if you have a question, I'm going to ask you to raise your hand, and I will come to you with a mic because we want to record your questions for posterity on YouTube, so that those who are listening to the tutorial and following online, believe me, people do it, and I've done it before. They can know the context of what Hugo is going to be blabbering about, all right? So please make sure, if you have a comment or a question, raise your hand, and I will come to you with a mic, and that way we'll have it recorded.
And I will be blabbering. Yes. Consistently. Firstly, I just want to thank PyCon for accepting this tutorial. Both Eric and I are really excited to be teaching it. Eric and I have been talking about this type of stuff and teaching this type of stuff for several years, for 3 years together now. And we first taught, I suppose, what is a foundation of this workshop last year at SciPy in Austin over the summer, which was really exciting. So I'm really happy to be here teaching with Eric again. And I also just want to thank all of you for coming in and taking an afternoon to learn this stuff and be interested in this stuff. I really appreciate all of you being here. So we're here today to have an introduction to Bayesian inference, essentially through the world of and lens of simulation and telling stories. And we're at a very kind of interesting point in time where we have a lot of fantastic computational tools to think about probability, which weren't around 20 years ago, definitely weren't around 100 years ago when people were developing all these frequentist tools. And so it's actually a very exciting time to be thinking about these things. And one thing that we're going to do today is think about how to talk about probability, how to think about probability, not using calculus and equations, but using random number generators, NumPy's random number generators, and telling stories of probability distributions, which I personally find very, very exciting. So we're going to start off with a bunch of probability via simulation and random number generation. Then we'll move into conditional, joint probabilities, or using a lot of different data sets. And in the second half, we'll wrap up the first half with Bayes' theorem, and then we'll start thinking about Bayesian inference and how to compute these types of things and answer data-centric and scientific questions using the formulations of Bayesian inference. We'll be doing that via simulation once again, and time permitting, and I'm pretty sure we'll get there, we'll wrap up with an intro into the wonderful world of probabilistic programming languages, which I find very exciting because as opposed to most programming paradigms where you have first-class citizens such as ints and strings, or in data science, data frames and arrays, in probabilistic programming, your first-class citizens are probability distributions. So we get to work with them directly, which is super cool. So maybe to get started, I suppose the other thing to mention is that there's going to be a mixture of live coding, which we'll see how that goes. And, oh no. Okay, sorry, yeah, this is, it's the wrong direction. Okay, so we're just going to execute the first cell to import all our packages. We'll be using some NumPy, some Pandas, Seaborn, which is data visualization for a few things, Matplotlib, which is data visualization. This matplotlib inline command allows plots to appear below cells as output of cells. SNS.set is, you see I've imported Seaborn as SNS. SNS.set makes figures look nicer, essentially. So we're going to start with part 1, although I really, because it's PyCon, we should start with part 0. That's a zero indexing joke if nobody got it. So in part 1, if you have to explain a joke, there's a problem there. So we're going to develop an understanding what probability means in both Bayesian and frequentist terms. We're also going to start simulating probability distributions that model real-world phenomena. Then we're going to look at how probability distributions relate to data-generating stories. So the data-generating processes and how can we describe them in words and some numbers, but not a lot of equations. Then we'll look at joint probabilities and conditional probabilities, and then we'll understand Bayes' theorem and its utility. Okay, so the first thing, and I want to say, and there's a bit of overhead, conceptual overhead here, but it's worth going into. People think about probability in a multitude of ways, and pioneers such as Bernoulli, Bayes, and Laplace thought about probability as a degree of belief or plausibility, like how much do I believe this thing to be true, based on the evidence that we have at hand. That seemed like a vague notion at the time, and there wasn't actually a lot of computational power to figure out how to formalize this that we have now and we'll see now. So what happened is the statisticians of the time redefined probability as the long-run relative frequency with which an event occurred, given a lot of repeated experimental trials. So you experiment, you get a lot of data, and then whatever proportion you get there is a probability of some sort. You can think about error bars or uncertainty around that. But it's something that can be measured is the point. And it was then seen as an objective tool for dealing with random or stochastic phenomena. This book, which I got this quotation from by Sivia and Skilling, is a must-read for anybody interested in this type of stuff. It's a really beautiful, short, and more comprehensible, more understandable book than a lot that's out there. So when we're talking about this type of random phenomena, you know, we can be talking about so many types of things, such as click-through rate on a website. This is a nice example because if we know that a website has a click-through rate of 10%, we can then calculate the probability of having 10, 9, 8 people click through it upon drawing 10 people randomly for the population. But that's not the type of question we usually ask in science, right? In science, we usually say, given the data of how many people click through, how can we calculate the click-through rate? And then how certain can we be of this calculated click-through rate or this estimate? Or how likely is a particular CTR, click-through rate? So I've written this here, but I'm actually going to write this on my makeshift whiteboard. Pull this over here so I'm still close to the microphone. Oh, that's great. This is embarrassing. Yeah. Thanks, man. There we go. That's why they call us a team. So essentially, what I've told you is that we're quite good at computing the probability of seeing data, seeing how many people click through, given, and all this line, this means conditional on, we'll see what that means a bit more later on, but given a model, we're pretty good at calculating the probability of the data. But in science, we're very often interested in the probability of the model given the data that we've collected, okay? And moving between these two is essentially highly non-trivial, but Bayesian inference provides a really kind of robust and interesting way of doing that, okay? So we'll start thinking about probability by exploring questions of the first kind. So the probability of data given an actual model. Thanks, man. And to do this, we're going to start writing some code, okay? Random number generators. So the framing of this question is, let's say that a website has a click-through rate of 50%. All that means is that 50% of people click through, right? So if we pick 1,000 people at random from the population, how likely would it be to find that a certain number of people click? I'm just going to edit this slightly. Okay? And what we can do is we can simulate this. We don't necessarily need to use equations, right, at this point. We can simulate this using NumPy's random number generator, okay? So before we do that, though, I'm going to say we're first going to use NumPy's random.rand to randomly select floats between 0 and 1. This is known as the uniform distribution, okay? So we're going to do this. So, and this is, code along, right? Okay. So np dot random dot rand. And how many did I say? Let's do 1,000. And now I want to plot a histogram. The reason I've got the semicolon after this, you may be aware, is there's some text output that we want to avoid, okay? Okay, so there we go. Now, I'm sure a whole bunch of you who work in science have been like, label your axes, and I totally agree. We're not going to do that for the sake of time currently, but I totally admit that this is like bad practice to not label axes here. Okay? So, we've got a uniform distribution, but how does this tell us about how many people click through, right? We can actually use this random number generation process to figure out how many people click through given a particular rate. The way we do this is, as we've got uniform numbers between 0 and 1, to simulate sampling from the population of people clicking, we check whether each float was greater or less than 0.5, okay? If it's less than or equal to 0.5, we say the person clicked through. And this is generalizable to any click-through rate, okay? So let's compute how many people clicked. What was the original variable? It was x. And I said less than or equal to 0.5. Can anyone tell me what clicks will be? So x is an array. What will clicks? It'll be an array of true or false, of booleans, right? Now the cool thing about booleans is they've got arithmetic operations, so we can add them together. So if someone clicked through, it's going to return true. If someone didn't click, it's going to return false. So if I sum together that array, that'll just give me the number of people who clicked through, right? That's pretty handy. So sum, the number of clicks is the sum of clicks, and then I'm going to print it out using f strings, which, so let's do that. Yep, so the number of clicks was 518 out of 1,000, which isn't quite 50%, but remember, because we're simulating a phenomenon, we wouldn't expect it to be exactly 50%, right? A little note about F strings. F strings, it's pretty cool. It was introduced in Python 3.6, I think, right? And it allows you to include variables within strings very nicely. I joked once that it was the best thing about Python 3.6, but I'll never joke about that at PyCon ever again because people are pretty opinionated. Okay, so we've got the number of clicks. Now I want the proportion of clicks, right? Okay, so to get that, we're going to get number of clicks and divide by the total number of people, and I could divide by 1,000, but just in order to have it generalizable, the code, I'm just going to, do it by the length of clicks. Okay. So up for discussion, I always do this. The question I had, did you get the same answer as your neighbor? And the answer is probably no, because I've already told you why. Because we're simulating a random process, and there'll be some variation with respect to that. Okay? So let me ask you this. Let's say that all you had was the data. We didn't know what the click-through rate was. We didn't decide it a priori. All you have is this data, and you want to figure out the click-through rate. So that's really the probability of the model given this data. What would your estimate for the click-through rate be, given the data that I have up here?
I'd estimate it be to 1/2, 0.5.
Well, would it? Because look at the data has the proportion is actually 0.518, right? So wouldn't the estimate be 0.518? So all we have is the data, not the data generating process.
It would be whatever each of us sees on our screen, given some error, right? I mean.
Yes, so that answers my second question. My first question is, what would your point estimate be? What would your estimate be? And it would be what you have on your screen. Now, how confident, what would your error bars or confidence interval around this be?
My error would vary by my sample size. So smaller sample, bigger the error.
Yeah, exactly.
Standard error concept.
And essentially, what we'll see at some point, well, maybe not today, it depends how far we get, is that the error will vary with respect to the square root of the sample size. 1 over the square root, in fact. But the issue is that doing it in this fashion, we have no idea what the error is. What we'll see in a Bayesian framework is that we get out this estimate, and we actually get a distribution of all the possible click-through rates. And from that, we can actually draw out any information we want about this particular value, which is really cool. Okay. Now, just as a note, I've called it a note there. I think I called it a keynote last time, which doesn't make sense at a conference. So we've described probability in 2 ways. But we haven't described it mathematically, okay? And we're not going to do that today. We're going to think about probability as a way of thinking about data generating processes in the world and use random number generators to simulate them and see how that corresponds to our data. Okay. If you're interested in the mathematical descriptions, essentially, well, what I'll say is that probability defines a function from the space of possibilities, possible values. In the above, it's the interval 0, 1. That describes how likely it is to get a particular point or region in that space. Michael Bedencourt has an elegant introduction to probability theory that I can recommend if you're interested. So, all that having been said, it's time for hands-on. I'd love to take 5 to 10 minutes for you to use random sampling, as we've done above, to simulate how many people click when the click-through rate is 0.7. How many click is one question, and what proportion? So get coding on that, and when you're done, put up the green sticky, and if you have a question, put up the red one. Yeah.
And if you're done with the exercises, feel free to move on. This is a habit that Hugo and I have had. You can always go beyond us.
But please do remember to put up the sticky just so
And
we have an
yes, make
indication
sure you
of how
put
many
up the
people-
stickies.
Yeah. And actually put it on your forehead, not the computer. No, I'm joking. That's a ridiculous idea. Okay, we'll have one more minute. I see a bunch of green stickies coming up. And if you're having any challenges, Eric's going around. I'll also say that it's quite similar to the solution for the 0.5 that we went through together. So, okay, great. This is exciting. So let's see if I can do it. Good. So use random sampling to simulate how many people click through. You can sample from the uniform distribution once again. I'm going to be slightly lazy and use the same random numbers that I generated before. Okay. So because the click-through rate is 0.7, we're looking for all those that are less than 0.7. Number of clicks was the sum of clicks, remember, because we have that Boolean. So I got something in my throat. Number of clicks, and then once again, how do you get the proportion? Can someone tell me? It's not a trick question. What's that? Exactly, so it's the number of clicks divided by the length. The total number of people. Perfect. Whoa. I'm not into that. There's a very low probability that you will get, right? Wow. Okay, cool. I like it. It's an omen of things to come. Okay, great. So now we've generated some stuff. I just want to discuss some similar principles with real-world data. You can calculate these types of proportions or proxies for probability with real-world data. And we're going to look at the Galapagos finch beaks, which several people went over many years to measure the lengths to the islands of, I think this one is the island of Daphne Major, but I'd need to confirm that. All the data is here, this hyperlink. Okay, so these are measurements from 2012, so I'm going to call it DF_12, right? Okay, so, and we're just printing out the first 5 rows here, which I would urge people not to do, actually, do it now, but I think someone asked the question a while ago, like, how many mistakes do you think are made in data science just as an artifact of people looking at the head of a data frame first? Right? Worthwhile question. Don't have time to think about it right now because we're here for probability. Okay, so I just want to take out, the lengths, and this is B length for beak length, right? And we'll see, band doesn't matter, we'll see the species. There'll be 2 species. We have the beak length and the beak depth. So we're going to do that. Now the question is, what proportion of birds have a beak length greater than 10? So we can do exactly the same thing as we did before, where the proportion will be, we'll look at the lengths, that are greater than 10, and I'll need to divide that by the total length of so many lengths happening. Whoa. Yeah. What have I done here? Yeah. Yeah, I do. Thanks. Lucky I got you here. Okay, 85. Just over 85% have lengths greater than 10. Yep. Absolutely. How is that?
That's better, thank you.
Okay. And just, if you just give me one, okay, no, we're going to keep going and then I'll figure this out in a second. So, what I want to say is that this is the proportion of birds in your sample, in our sample, that have a beak length greater than 10, in the empirical data, not the probability that any bird drawn from the population will have this beak length, okay? So always remember, sample is different from population. Okay, but we can use samples to think about proxies for probability. And one way to do that, which we'll mention now, see a bit more later, is via resampling. So essentially, what we do is we look at this data set that we have and treat it like, pardon me, we treat it like a population and draw new data points from it. Okay, so thanks. We'll simulate drawing random samples with replacement. So we'll draw one, put it back, then from the same set, draw again to see how many lengths are greater than 10 and calculate the proportion. And this is something known as, well, it's been dubbed as hacker statistics because we're essentially using computational hacker techniques to think about statistics. And you can get distributions out this way, et cetera. So we're gonna, let me get this right. Yep. So what I'm going to do is I'm going to draw 10,000 different data points out of our sample, which is actually quite smaller. But so we're going to take the sum. Now, to randomly sample from it, we're going to do np.random.choice. Now, we're sampling from lengths, right? Now, how many do we want? The next argument is the number of samples. And we want to be able to do it with replacement. So we're going to set the keyword argument replace equal to true. Now, this will give us 10,000 samples, and we want to see how many of those are greater than 10, okay? And then divide by the number of samples, okay? And once again, we see something quite close. Now, the reason I wanted to mention this now is we've got not just a proportion, but a proxy for probability. Now, the really cool thing is, if we can, what I just did and what you just did, I just love that you've got a green sticky on your head still. It's awesome. It's really, really positive. What we can do is we could do this procedure 1,000 times and get out a variety of different results, and that will give us a distribution. So we'll know more about uncertainty in that sense as well. But we'll say a bit more about that later. Now it's time to get to some really fun stuff. Not that wasn't fun. It's just going to get funner. That's an Australian term for more fun, by the way. I don't know if people say funner in this great nation. So in the above, we've used the uniform distribution to sample from a series of biased coin flips. But some of you may know that these biased coin flips or click-through rates are actually called a binomial distribution as well, right? We've got a question up back. Just wait for the mic.
So I have a question to the validity of the method above, the resampling thing. Mm-hmm. So would you say that if we resample and do it many times, we know more about the probability now, or are we we use the data set which had just a very limited sample size, right? And now we resampled it and did it many times. Do we know more about standard deviation, standard error? I mean, what do we know actually now?
Yeah, you can get out, once you do that a number of times, you can get out standard deviation, you can get out standard error. Also, notice that we're not presuming any model, so it's actually a non-parametric technique for getting out the distribution. You can get out percentiles, you can get out a lot of different things.
And for this to be reliable, does the sample have to be like of a certain size, or like the initial
That's
set?
a good question. Yeah, there are certain. I'd suggest checking out Efron's original bootstrapping paper to figure out the actual. There are very few assumptions, but you know, sample size is important.
Okay, thank you.
Yep. Great question. Thank you. So let's think about the binomial. So with the click-through rate, I'm not sure that I mentioned that this can also be thought of as a biased coin flip, but this is kind of the more abstract model that people think about, is flipping a coin with probability of heads being 0.7 or 0.5, as we've seen, just as a click-through rate can be modeled as that. Incidence of disease also modeled as that. So it's quite an abstract model that's used in a lot of different places. More generally, the binomial distribution, it has two parameters, n and p, and it's defined as the probability distribution of the number of heads seen when flipping a coin n times, with the probability of heads being p, okay? And that's the story. That's the story of the binomial distribution. I could write out the equation for you, and you could, you know, work with that. But now we know the story, and we can simulate it. We can actually work with it in a lot of different ways. And as I wrote here, this distribution tells the story of a general model in the following sense. If you believe that you're collecting data in the world that has an underlying data-generating process with a binary outcome, and that one of the two outcomes occurs with probability p, then that story is the binomial story. So you can model your data using the binomial distribution. And what you can do, as we'll see, is not worrying about equations or fits or anything along those lines. You can plot what the binomial distribution would look like. You can plot your data and just eyeball and see whether it seems like a good fit initially. And we're going to be doing that time and time again. I'll reformulate this slightly and say that any process that matches this, is a binomial process, as I said. You'll also see individual coin flips referred to as Bernoulli trials in the literature. This is because this was discovered or created, this theory, by, I can't remember if it was Daniel Bernoulli or Jacob Bernoulli, but whichever one it was literally sat there flipping coins for days. Like, he did what we're doing, but flipping coins and writing down the results like tens of thousands of times. So we should all be grateful. Okay? Formulating this story in terms of Bernoulli trials, the story of the binomial distribution is the number R of successes in n Bernoulli trials with probability of P of success is binomially distributed, okay? So we're now going to use the binomial distribution to answer the same question as above, okay? And what I mean by that is we used the uniform distribution before, and we're going to see it as binomial. First, I'm going to set the seed. We're randomly generating numbers. Our computers use something that's known as a pseudo-random number generator. And what that means is that once I can set the seed, it's pseudo-random because once I set a particular seed, the random number generator starts from that point, and setting that seed will give the same random numbers after the fact. So if you and I set the same seed, then we'll get everything the same. And this is very important of course, for reproducible science. So I'm going to set the seed. What am I going to set the seed to be? Feel free to set the seed to be whatever you want, essentially. I'm going to set it to be my birthday. The way that we write birthdays and dates in general. It's weird that you all know my birthday now, but feel free to reach out on July 16 with wishes of prosperity and happiness. Okay, so the cool thing about simulating stuff is we did np.random.rand, or you can also do uniform, but we did rand before. np.random. If we're doing a binomial distribution, does anyone have an idea of what the function is going to be called? Binomial, yeah, definitely not a trick question. Okay, so, and that's pretty cool. And we want to flip the coin 10 times, right? and P is 0.7, so that's the second argument. And look, come on, seriously. I really didn't want to get 7 there, but this is some black wizardry we have here. But okay, what we'll see though is, so that's if we do this binomial trial once, okay? If we flip a coin 10 times, now we've got 7 heads. Unlikely, but you know, cool. And as I write here, in the above, we've simulated the scenario once. This only tells us one potential outcome. So let's now just simulate it 1,000 times, or no, let's simulate it 10. I don't even care. We can simulate it like 1,000,000 times and see what happens, okay? So what I'm going to do is, I'm going to, once again, and this is one of the great things about NumPy random, is that I can do the same as I did before. So I've got 10. Let me just get this right. 10, 0.7, and now I can just choose to do it as many times as I want. So this will be the size, okay? This is the number that I get out, okay? And then I'm going to plot the histogram. I'm going to plot it normalized, so we get a density, we get a fraction, a proportion, essentially. We'll see what that means. Okay. Cool. Yep, this is nice, right? So we'll see, and I'm actually, just for clarity's sake, I'm going to just print X here. We'll see X. Before this just gave out one number, now it's actually going to give out 10,000 different results, okay? So X is an array of all the 10,000. We're plotting a histogram of that. And what do we see here? I mean, we see pretty unlikely to get anything down here, but as we get more and more, we'll see 7 is the most likely, as you'd expect, and then it goes down and down and down, and 10 is the maximum you'll get, right? Okay, so that's pretty cool that what Daniel or Jacob Bernoulli, I mean, they were brothers, they probably flipped coins together. That was a weird remark. We just got to do 10,000 sets of 10 coin flips using our random number generators and getting out this normalized histogram, which is pretty cool, okay? Once again, I answered the group chat. What do you see in the above? And the point is there's a peak at 7 and it goes down on either side. So having said that, it wasn't so unlikely that we got 7 there. I mean, it was the most likely. Okay, all that having been said, I think what I'd love for you all to do now is to use the tools that we've just developed to start flipping some bias coins and answer these questions. So the first one is, if I flipped a bias coin with probability of heads 0.3 20 times, what's the probability of 5 or more heads? And then there's a similar question, and then I'll get you to plot something. And I'll give you 5 to 10 minutes to do that. So take down your green stickies, please, if they're still up from before. And then, get coding. So if you get stuck at all, just go back and look through some of the stuff we've done together. Remember, there are clues everywhere. It's my new mantra. All right, we'll take a couple more minutes. And then as a teaser, things are about to get really fun with, we're going to have a battle between histograms and empirical cumulative distribution functions. Spoiler, ECDFs win. All right, everyone, I'm gonna get moving on this. So, I'm flipping a coin 20 times, probability 3. So once again, I'm gonna be doing np.random.what? Binomial. This is great. It's like a call and response. I don't even know if that was a hip hop reference or what that was. And look, I'm going to do this experiment 10,000 times. You can do it as many as you want, essentially. And I want to know when that's greater than or equal to 5. That will give me the Boolean, so I want to sum that up. And then I want to divide that by the number of times I did it, okay? Okay, good. That's the probability of getting five or more heads, okay? Now, similarly, calculate the probability of 5 more heads for p is equal to 5. I'm going to get a bit lazy here and just copy and paste, right? If you copy and paste 3 or more times, what do? You write a function. Thank you. Great. Eric will tell you that as well. Okay. So if you flip a fair coin 20 times, the probability of 5 or more heads is 99.5, and that makes sense. I mean, you know. Okay, so plot the normalized histogram of number of heads, flipping a fair coin 10 times. Okay, I think I can do that. It'd be really embarrassing if I just couldn't for a long time. The rest of the workshop was me trying to do that. Okay, so doing that, okay, 10 times, fair coin. Now I'm gonna plot the histogram of x. Because I want it normalized, I'm gonna do density equal true, and I'll set the number of bins equal to 10. Okay, probably need to close that out. Okay, cool. Did most people get something like that? Cool. Quick question. Does this look like anything for you, to you? It's a binomial distribution, but does it look like any other? It looks kind of normal or Gaussian-y, and that's telling. And we may not get to this in this workshop, unfortunately, but in certain limits, the binomial looks Gaussian. You can prove that in a number of ways, one of which is the central limit theorem. What we will see soon is the limit in which the binomial distribution turns into the Poisson distribution, which is really cool. Okay, so this is a key point now that I don't want to spend a lot of time on, but you may have noticed that the binomial distribution can take only a finite number of values, whereas the uniform can take any number between 0 and 1. And these are different enough to make mention of them. The former is called a probability mass function. That's where you have a discrete number of possibilities, and the latter a probability distribution function, or PDF. Going on, we may discuss this a bit more, but I wanted to make that very clear. And once again, Sevier and Skilling is a great reference for this. I'll also provide a link, maybe in the next iteration, a lot of the work of Alan Downey, who we'll probably see some of his stuff later on. He does a lot of incredible work on this stuff. So, I have a question for you. Looking at this histogram, can you tell me the probability of seeing 4 or more heads? Can someone easily read off that histogram? So you'd like, the way I'd do it, and if like this is my naive way of doing it, I'd like add up like the proportions across 4 or more or 3 or less, and then subtract that from blah, blah, blah. That seems like hard work to me, and it seems kind of counterintuitive. I'm just wondering if there are any other types of figures that could help us with this. And lo and behold, enter the empirical cumulative distribution function, which is one of my favorite plots. And empirical, and we're going to be building a lot of these actually. It's an alternative to a histogram. It's a way to visualize univariate data, so data of one variable. And the ECDF is super rich in information. So it allows you to visualize all your data. There is no binning bias. And some people think binning bias in histograms is, a very like archaic or not relevant problem, but in terms of even thinking about, multimodality of distributions or where these things occur, you can tell a lot of lies with histograms, right? By choosing bin sizes inappropriately. So you avoid binning bias with an ECDF. So you plot all the data. You can also plot controls and experiments. You can plot data and models, which really means many populations. You can see multimodality, though it's slightly less pronounced. And if you think, what we'll see is that for the more mathematically inclined, an ECDF is the integral of, is that right? Yeah, integral of the PDF. And what happens when you integrate, modes or peaks become points of inflection, okay? So you see that there. And you can just read off so much stuff from ECDFs, such as percentiles. I would really advise you to see Eric Ma's great post on ECDFs here, and this Twitter thread, thanks to Alan Downey. And Eric, I'm telling you I love ECDFs. If you speak to this guy about ECDFs afterwards, and you'll come away with a different worldview, I think. I just want to show you one thing that happened recently. I saw a really bad histogram in a paper a few weeks ago on Friday afternoon before lunch. And so before going out to lunch, I just tweeted out 3 words. I tweeted out, "Stop plotting histograms." And I went to lunch and came back to essentially a lot of abuse. So yeah, this is, I don't know why it thought I was in that time zone. Maybe it's because I set up Twitter in Australia. But, you know, stop plotting histograms. Someone wrote, can we stop Brexit first? Fonsbeck wrote, plot several histograms. Michael Betancourt, good friend of mine, threatening me with fighting. And then he keeps going on. Then I start swearing and saying, let's teach people more broadly. You're the guy who, you know, and it just goes on and on and on. Andy Muller, core dev of scikit-learn, you know, like it's, yeah. Essentially, I just left it alone and saw the whole Twitterverse attack me, and I left it for a day. Then people started defending me. Then people started attacking again, and it's just, Twitter's a beautiful place, isn't it? Enough about that, though. Okay, so to define, please, Eric.
Sorry, I just wanted to make one point of clarification. It's that it's not the ECDF that is the integral over the PDF of a probability distribution. It's just the CDF. Yes, the cumulative distribution function is the integral of any continuous probability distribution's PDF. All right, so if you take the derivative of the cumulative distribution function, which runs from 0 to 1, you will get back the probability distribution function.
And we'll see that. And I suppose the point is that the empirical cumulative distribution function is from data, whereas the cumulative distribution function is from a probability distribution, okay? So to define it, in an ECDF, the x-axis is the range of possible values for the data, and for any given x value, the corresponding y value is the proportion of data points less than or equal to that x value. Okay. Now that's a bit of a mouthful, but we're gonna make one now. What I'm gonna do first though is define a handy ECDF function that takes in data and outputs the x and y data for the ECDF. So what we do is we compute the number of data points, then we sort the data. And then we take the y data for each data point. So I'll just get you to execute that cell. Now, what I want to tell you is that I'm going to get you to do this now. Actually, no, I'm going to do this, and then you can plot ECDFs later on. That's great. I think the first time I should demonstrate. So we've got, okay, this has to be thee, not he. Okay. So we generate x and y data for the, so this is for the following, for the previous question, I'm sorry. Please read the answer to the following question. Is that what I wanted? Yeah, so I want the previous data, okay? So to do that, remember this ECDF function just takes in the data, so I'm going to do ECDF x, okay? Now I'm going to plot it. plt.plot. Now the x data is x flips, y data is y flips. Now I'm going to add a few more little quargs, keyword arguments. It'll create a line, and I don't necessarily want a line per se. So I'm going to have dots as markers, and I'm going to have line style equal to none, okay? Let's just do that again. Okay, beautiful. Once again, I haven't labeled my axes, but that's okay. So what we actually see, the question is, what's the probability of seeing 4 or more heads? So these are the number of heads in these trials, and we'll see that the probability of seeing 4 or more heads, okay, the probability of seeing less than 4 heads is 20%, right? So the probability of seeing 4 or more heads is 80%, okay? Yeah, 80%-ish. Yeah, it's actually just like, it's probably 82 or something like that. And you can do that calculation. But having said that, you can read off the median, you can read off all types of percentiles, your 95 percentile, your 25, your 75. You can read off all your percentiles and do all of these types of calculations as well. Eric.
And I want to add one more piece. So for those of you who are in the network analysis tutorial, whatever I said there, Hugo has just repeated. And looking at this, there's even more information that you can get for the case of a discrete probability distribution, which is what we have here. If you look at all the points stacked up, the height tells you the amount of credibility associated with that number, the probability associated with that number. So which is the most probable number? The one that has the highest amount of height. Try reading that off a histogram, fighting words.
Yeah. I like it. See, that's what I'm talking about. I'm the good cop.
I guess you could also use just the histogram and add the cumulative equals true parameter, and you would get the same thing, right?
Yes, but you would still have the binning bias if you didn't bin correctly. So if you're, yes, exactly. And there's a question behind?
Okay, great. And so the one thing I want you to notice here, let's say I had 10 different populations. I could plot them all in different colors or different transparencies here. Try doing that with I mean, you see histograms of people plotting like all of these overlapping things. But I could plot a model here, as we'll do, and then control an experiment. But okay, I want to move on to really, we've talked about probability distributions and some of their stories. I really want to get into this now. Before I do, though, I want to thank Justin Boyce, who is a very old friend and collaborator. He's appeared several times on a podcast that I host called Data Framed that I'd all urge you to listen to help me meet my KPIs at work, essentially. I know they're OKRs now, whatever. But Justin and I have spoken, it must be for 100 hours, about this type of stuff. And the material he's developed, so he's a lecturer at Caltech teaching this type of stuff. The material he's developed has changed the way I think about probability, simulation, and telling stories. So I want to shout out to him. I also want to say I think some of this I actually just directly plagiarized from him, but I think the license he used allows me to do that. So it's all good. Okay, so once again we saw we can match data generating processes with binary outcomes to the story of the binomial distribution, given another this characteristic of Bernoulli trials. Now I want to tell you about the Poisson distribution, how we can think about the Poisson distribution by telling stories, okay? So there's a great book by David McKay called Information Theory, Inference, and Learning Algorithms. He tells the story of a town called Poissonville, in which the buses have a very odd schedule, okay? So if you stand at a bus stop in Poissonville, the amount of time you have to wait for a bus is totally independent of when the previous bus arrived. So what this means is you could watch a bus drive off and another arrive almost instantaneously, or you could be waiting for hours. Now this seems like it probably wouldn't happen. I live in New York City, and the subway system does operate like that, I feel, a lot of the time. Having said that, there are a lot of natural processes which follow Poisson processes. So natural births in a given hospital, okay, is one. There is a well-defined average number of natural births per year, and the timing of one birth is independent of the timing of the previous one. Why is it important that I said natural births? You can't schedule them. And if I said births in general, it wouldn't be true, because induced births actually happen with respect to certain schedules of doctors' availability, nurses, like a lot of different things play into that. So they're not Poisson processes. Landings on a website can follow Poisson processes. Meteor strikes, molecular collisions in a gas, aviation incidents, and any process that matches the buses in Poissonville story is a Poisson process, okay? So what then is a Poisson distribution? A Poisson distribution is the number of arrivals of a Poisson process in a given amount of time, okay? And it has one parameter, the average number of arrivals in a given length of time. So to match the story, we could consider the number of hits on a website in an hour with an average of 6 hits per hour, this being Poisson distributed, okay? Now what I'm going to do is I'm just gonna generate that data now so we can see what it looks like, okay? So what I've said is the Poisson distribution has one parameter, the average number of arrivals in a given length of time. So I'm gonna generate np.random. So if it's a Poisson distribution, what do you think the next? It's not a trick question. It's Poisson, but lambda will, yeah, so lambda is the variable, but the name of the function is Poisson, and I can just use a positional argument. I don't need to use a keyword argument. I'm going to use the size equal 10, let's just say 10 to the power 6. Now I'm going to plot this, samples, and I'm going to choose 21 bins. Yep, didn't work. Bins. Okay. Cool. So this, if I take this many samples, is what our Poisson distribution looks like. And you'll see that, the average is around 6, the average of 6 landings on a website in 10 minutes. So what we've done, we can write down the equation of the Poisson distribution for sure, but we've actually rigorously defined it using a story and able to simulate it now and understand it without using the math or the calculus. And I actually think this is incredibly powerful, and it will allow a lot more people to it reduces the barrier to entry for people who don't necessarily have a serious background in calculus. Question, does this distribution look like anything to you that we've seen before or you've seen before? It's kind of normal. It's not quite, because it's definitely not symmetric, but I can see why you'd say that. What's one we've seen earlier today that was kind of normally but not symmetric? Binomial, right? It's kind of binomial-esque, okay? That's a new term. Okay, and in fact, the Poisson distribution is the limit of the binomial distribution for low probability of success and large number of trials for rare events. And I've written this here, but I actually want to go through it. So let's think about, this is one of the greatest things about telling these stories. You can show that in the limit of low probability and large number of trials, you can show mathematically that the binomial and the Poisson converge, or they're approximate, right? But you can also do it just by telling the stories, okay? So think about the stories. You're doing a Bernoulli trial once a minute for an hour, each with a success probability of 0.05. You do 60 trials. The number of successes is binomially distributed, and we'd expect to get about 3 successes, right? So this is the same as the Poisson story of seeing 3 buses on average arrive in a given interval of time. And what this means is that the Poisson distribution with the arrival rate equal to n times p from the binomial distribution approximates that binomial distribution, okay? The reason this can be useful practically is the Poisson distribution can be simpler to work with because it only has one parameter instead of 2. So what I'd love for you to do now is just have a quick hands-on. You get to plot your first ECDF by yourselves, not coding along. So please plot the ECDF of the Poisson distribution that you generated above. And I'll give you a few minutes to do that. Oh yeah, so take down the stickies until you put them back up. But everyone looks like we're doing really well. You all seem to be naturals at ECDFs. I like it. Okay, so I'll hopefully I can do it as well. So, right, so we've created that pretty cool utility function. Oh, and by the way, that function is thanks to Justin Boyce as well. That's something I think I edited slightly, but I got from him. So we're doing the ECDFs of samples, and then we're going to plt.plot. And this is a pattern, right? This is what we're doing quite often. X, P, yp. And remember, we want dots and not lines. So we want marker is equal to dot, line style is equal to none. Whoa, dude. Okay, cool. Look at that. That's the ECDF of our Poisson distribution. That's exciting, huh? So, the next thing I'm going to do is actually some of the most fun. And this is taken explicitly from Justin Boyce. And we actually discussed this example on the podcast. He called me one day and he was like, Hugo, I just figured out that LeBron James's field goal attempts are Poisson distributed. And I was like, that's really cool, man. Let's talk about it. And he showed it to me and I said, come on the podcast. We chatted about it. So once again, let's first remind ourselves of the story. The number of arrivals of a Poisson process, I can edit that later, in a given set of time is Poisson distributed. And to quote Justin, he said to me, we could model field goal attempts in a basketball game using a Poisson distribution. This is because when a player takes a shot, it's largely a random process being influenced by myriad ebbs and flows in a basketball game. Some players shoot more than others though, so there's a well-defined rate of shooting, an average for any given player. So let's look at LeBron's field goal attempts for 2017-2018 NBA season. This is the data that I've just written here. You can get it from there. Okay, so we're going to execute that cell. So now to show that this should not be there, to show that LeBron's attempts are approximately Poisson distributed, you're now going to plot the ECDF and compare it with the ECDF of the Poisson distribution that has the mean of the data. And the question is, why do we want to compare it with the one that has the mean of the data? It makes intuitive sense that we don't want to plot a theoretical Poisson distribution that's wildly away from it. Essentially, in the end, though, and we can go into this later, it is the maximum likelihood estimate given the Poisson model. I've called this a hands-on, but I'd actually, this is so much fun to do. I want to do it with you all, and then we can move on. So we're going to generate the X and Y data for the ECDF. So that will be ECDF FGA, okay? Now, what I'm going to do, instead of just plotting LeBron's ECDF, I'm going to plot, instead of just plotting LeBron's ECDF and one simulation of the ECDF of the Poisson, I'm going to plot a lot of different simulations of the Poisson. I'm going to do it 1,000 times. Make it the transparency relatively low so we can actually see what it looks like with some sort of spread, the different types of possibilities of the Poisson distribution when you sample from it, okay? So, number of times we simulate the model is 1,000. Then I plot the ECDF of the data. Now, I want to plot the ECDF of the model, okay? Now, to do that, what I want to do is np.random.Poisson. Now, what I want to use is, remember, I want to use the mean of his field goal attempts, FGA, and I also want to say how many I want to generate, and I'll just, for the size, I'm actually going to use the length of the LeBron data as well, so we get something analogous, okay? Now, I want to plot that simulation. So I want to generate the ECDF of the simulation. We get samples there, and then I plot it in the for loop, and then look, I label my axes. It's the first time for everything. Also, like, I'm slightly uncomfortable like plotting 1,000 times in a for loop, but for pedagogical purposes, I'm less uncomfortable with that. So fingers crossed that we're going to see something cool here. Yeah, look at that, okay? So the gray, remember I had an alpha and light gray. These are all the simulations of the Poisson distribution in the gray. And here within, in the dark, it's LeBron's attempts. So what you actually see there is that his attempts pretty much right in the middle of all these simulations of the Poisson distribution. So you can really see from the ECDF that his attempts are approximately Poisson distributed, which is pretty cool. So we've seen a few stories now. There were 2 more stories, time permitting, I'd like to talk about, and then, this is kind of an elongated introduction to probability through storytelling and random number generation and simulation. We're here for Bayesian inference, and we're going to get to that, of course. But I want to tell a few more stories of probability distributions and then really get into the meat, okay? So we've seen a number of discrete distributions, Poisson, Binomial, all of these take on a set of discrete values, right? We also have a lot of continuous ones. The 2 we'll talk about are the exponential and the normal or Gaussian distribution, which we've seen, okay? So I want to tell you what the story of the exponential distribution is, okay? The story is, we've seen that if we go back to Poissonville, the number of buses that arrive per hour or per interval of time are Poisson distributed. The exponential distribution has the following story. The waiting time between arrivals of buses are exponentially distributed, okay? Once again, you can prove this using math. You can take the definition of a Poisson process and then show that the waiting times between events are exponentially distributed. You can also do it via simulation. I'm going to tell you the story for the time being, and then we're going to check out an illustrative example. But I'll just repeat, the waiting time between events of Poisson process are exponentially distributed. It has a single parameter, which is the mean waiting time, and the distribution is not peaked, as we see from its PDF. I'm not going to draw it, but most of you know an exponential distribution goes like that, right? Okay. Okay, so let's now look at the time between all incidents involving nuclear power since 1974, okay? Now, if these follow a Poisson process, we could expect the waiting times to be exponentially distributed, right? So to see if this story is even credible, we can plot the ECDF of the data with the CDF that we'd get from an exponential distribution with the sole parameter, the mean, given by the mean time between incidents, right? So there's just a bit of like pandas crap happening here in order to get out intertimes, which are the actual times. And afterwards, I'll give a reference for this data, okay? So first, we'll code along here, but I'll ask, we want to compute the mean. How do I get the mean? Does anyone, the mean of a NumPy array? np.mean, yeah. Interactive workshop. Intertimes, okay? Now, I want to sample from the exponential, right? So to do that, so np.random.what? I'm sampling from the exponential, right? So it's all, I'm going to ask this every time. And it's always going to be the name of the distribution. And we'll see why that's also important when we get to Bayesian modeling with PyMC3, okay? So, and it's also important to recognize that this is great design. There are certain problems, design problems with the SciPy stack in some respects. There are also a lot of beautiful design principles, such as making, the random module this intuitive to use, okay? So props to whoever did that. Okay, let's take a whole bunch of them. Okay, so I want to get the ECDF for the sample. Sorry, yep. I've done something bad here. I've called it sample. So for data and model is actually sample. There, okay. So ECDF, and this is intertimes. And here, I want the ECDF of the samples, okay? Now, the moment of truth. So I want to plot the ECDF. I want to plot the CDF for the model. So that'll be X there, Y there. Okay. And I want it to be lines because it is a continuous CDF that I want to see. And then I'll plot this, okay, which is the data. Okay, so look at this. Here we have the model. This is the exponential distribution with the mean of the data. And this is all the data plotted on top of it, okay? Now, you can go and do your statistical tests and tell me your p-values and whatever you want to do there. Please don't, actually, but you could. But you don't need to. I mean, depending on your use case, you really don't need to, because you can see how close this data is to being exponentially distributed, which means that we can model the nuclear incidence as a Poisson process, okay? Now, before getting on to conditional and joint probabilities, I want to talk about the normal distribution, and maybe after we do this, we'll have a break, then jump back in. The normal distribution, you'll also know as the Gaussian or bell curve, appears everywhere. It's the most used distribution. It's the most misused and abused distribution. If there's any reason for doing Bayesian inference, well, there are actually many reasons for doing Bayesian inference. One really good reason is that, as we'll see, you need to bake all your assumptions into it, whereas in a lot of other, in frequentist methods, you can explicitly state your assumptions, but a lot of the time, underlying statistical tests are assumptions of normality that aren't explicitly stated. And that's very dangerous because a lot of data is not normally distributed, ran over. There are many reasons the normal distribution is all pervasive. One of the most important is that when doing repeated measurements, if I measure something a number of times, let's say I'm measuring something which I think has a true value, okay? I'm going to get a bit of error with each measurement, right? And we expect these errors to be normally distributed owing to the many sub-processes that contribute to the measurement. And this is actually because it's a formulation of the central limit theorem that I think Laplace gave originally, that any quantity that emerges as a sum of a large number of sub-processes tends to be normally distributed, provided that none of the sub-processes is very broadly distributed. We can talk about this ad nauseum afterwards, but I think it's important to recognize that this is a very important fact about why the normal distribution is so useful. Two other reasons are that it is in a certain limit. It does approximate the binomial distribution, which appears everywhere. And the third important reason is that locally around any peak of a distribution, I think a second order Taylor expansion will give you a normal distribution. So you can approximate the modes of symmetric distributions normally. Not just symmetric, actually, if you look close enough. Now, one of my favorite data sets in the world is the speed of light measurements in the Michelson-Morley experiment, okay? So what I've done below is I've plotted the histogram with a Gaussian curve fitted to it. So that's in there. You can just execute this cell. So I've imported the data. These are all the measurements taken, and we see that, you know, speed of light's somewhere around here. 299,000 kilometers per second. What's a megameter? Is that a thing? Okay, I'll find out. I'll be back about that. I'll check it out during the break. So it looks like, yeah, maybe these measurements are normally distributed according to the histogram, but maybe if I chose a different binning size, it wouldn't look normally distributed, right? Putting a model over a histogram, please never do that. Never do what I just did there. And so what you're going to do now is you're going to take, let's say 10 minutes, 5 to 10 minutes to generate that ECDF and plot it with the Michelson-Morley data. So if you remove your green stickies and then put them up when you're done, and I might add a few things. So the first thing to do is to generate the normal. Okay, I'm sorry, I'm just going to make a few more comments. That you're going to have to generate data from a normal distribution. What I'm going to get you to do is generate it from a normal distribution which has the mean of the data and the standard deviation of the data. And the mean I've already created for you as mean, and the standard deviation is STD there. So you're going to generate normal samples with the mean and the standard deviation of the data in this row. Yeah. And let's do it with 10,000 data points. Why not? So I'm going to slowly just start doing it myself as well. I just can't. I'm so excited. Okay, so I'm going to use np.random.what. Yeah, thank you for humoring me. Normal. And the first argument is going to be the mean, then standard deviation, then 10,000. On the other cool thing, I presume many of you, where's my toolbar? Many of you may know this, but you know, I've been doing a lot of like, you know, I know the first argument's mean, the first positional argument. I know the second positional argument is standard deviation. But if you didn't, you can check it out. There are help functions, but in particular, I like to use a bit of magic. So if I do this is IPython magic, right? Yeah, if I do a question mark followed by this call, it gives me the doc strings, it tells me location, scale, and it's really, location and scale are mean and standard deviation, but that's pretty helpful for those who haven't seen that before or would like a reminder. I'm going to delete that cell now. Okay, so now I'm going to generate the ECDF for the data. So once again, ECDF, and the name of the data is Michelson speed of light. Great name, great variable name there. And then ECDF samples. Now it's time to plot. And so I'll plot the theoretical first. X theory, Y theory. And then I'll plot the actual data. X, Y, and remember, I choose markers and line style accordingly, so it looks nice. Okay, so, yep, that's what I do every time. Okay, look at this. This is music to my soul. So we see the theoretical Gaussian normal distribution with the data overlaid. And so we see that it is, you know, very much, at least approximately Gaussian. Some people will ask me, but is it really normal? And the answer is probably not. I mean, you get enough data and it won't be normal, and your statistical test will tell you that. But at that point, if you have enough data, the model may not matter as well. So it really depends on what your actual question is. The point of this conversation was essentially to get us all working with telling stories of probability, matching it to distributions, and matching it to data to see what the data generating processes could be like. And in this case, I think that's very apparent. If you want to think about questions like, is your data, or I mean, Alan has written, are your data normal? Are your data normal? I'd urge you to check out Alan Downey's post, which is, are your data normal? Hint, no, which very much evangelizes doing a lot more than statistical tests to think about how your data has been generated in the world, okay? It's 2:45, and afternoon tea begins at 3. I've been instructed to let you out as early as possible at 3 because the food goes quickly, and I'm very cognizant of that. I'm just wondering if we have another 10 minutes. Because we could have a 20-minute break, but if the food starts at 3, that only gives 5 minutes of food, so.
How about questions for now? And I think it's a good time for discussion. There's a lot of concepts you covered, Hugo.
Yep.
And I think it's a good time to reflect on some of these fundamental things. So
Absolutely,
let's do
I agree.
Q&A for now. If nobody has questions, then I actually have a few summary points on just this part here so far.
Beautiful.
Some notes that I've been mentally taking. So where's the microphone? I put it back there. So first off, are there any questions on what Hugo has taught us so far? Get back there.
So we discussed basically very strongly on Bernoulli's distribution. So we
Could you
looked
speak
at
up? I can't.
Yeah,
I can't
so
hear.
for Bernoulli's distribution, we looked in a lot of details. One thing we didn't look at is like what's the probability of having a run of parallel events like 8 events or 10 events consecutively given a data set. So what's that probability? How can we calculate that kind of a probability in that case?
Yeah, so there is a probability distribution for that. I'm not remembering the name, but it's either one of, I think it's negative binomial or something like that is 10 times, and what's the probability of getting 8 heads in a row? Yeah. So for these kind of questions, I know that this is the reason why probability distributions are put at the back of most statistics textbooks, and that's where I would go to look that up. But you are absolutely right. Like that's the kind of generative story that we want to think about, to link what we think is the data generative process with a particular probability, generalizable probability distribution that we want to model.
That can be really high in case like having a parallel 8 events consecutively. We think that it should not happen, but we might find that it can be 0.9 or 0.85 or something very high. So is there a way to calculate if we can know like any function which can directly be used to calculate such kind of probability?
Could you repeat the question?
Yeah, like if there are 300, suppose there are 300 instances of Bernoulli experiment, head or a tail kind of experiment, what's the probability of getting like a 8 consecutive head or a tail after a certain point?
So the great thing about what we're doing here is you can simulate that and count it. I think Eric is right. It may be the negative binomial, but there is a distribution where you can, and it's in NumPy, where you can actually do it. But if there's a process that isn't actually a named distribution, right, such as a mixture model, for example, or 2 exponentials, one waiting for another, something like that, you can write out the function and the data generating process and simulate it as many times you want, and then do that count and get out that distribution yourself as well. So that's the power of this also. Does that answer the question? Great.
I'm sorry if this is a stupid question.
There are no stupid questions, only stupid. No, there are no stupid. That was gonna, yeah. You don't want to know where that was going.
So when you try to calculate the ECDF of the model, is there an analytical version of ECDF, or do we have to do the random sampling every time?
So as we mentioned, all probability distributions, especially the continuous ones, they have, you can analytically, if you know the PDF and you take the integral, then you have the CDF. And all NumPy distributions have the CDF implemented inside NumPy, like in the library. So you can do not NumPy, this is SciPy stats. So you do SciPy.stats.your distribution name .cdf, and you pass in an array for the support, which is the x-axis values, and you will get the exact curve that you want there.
You
So
can
that's the
see I've done
alternative
that
way.
here.
That's the way that Hugo did for that distribution there.
Yep.
Okay. Any other questions? Up front, Paul.
So I'm actually a recent convert to ECDFs because of the podcast where you had somebody on that talked about it, and so I Googled it right away, and there was some implementation that stats models just had, but it was all caps ECDF, and I was looking at the source code for that, and it looks like it does it like a slightly different way than the way we coded it.
Yep.
So the first part is just like, when you use it, do you code your own function for it, because it's pretty easy to do, and the second is there any bias to be aware of when you're using it? Because obviously with histograms, you have binning bias and things like that. Are there any areas where we should avoid using an ECDF?
So to answer the first question, I generally just have this boilerplate code I use.
I have a shortcut on text expander.
Amazing.
:ECDF, and it just pops out on my screen.
And I think several people, including Leland McInnes, is it?
Myself, Leland McInnes, and a few others, we want to put ECDFs in Seaborn, but
Yep.
Mike Wascom of Seaborn has been like, yeah, I just don't have the bandwidth to review it at this point. So
That's right.
for now, it lives as text expander shortcuts.
I'll say one major limitation of ECDFs, or why histograms are more useful. People understand how to read histograms. People at elementary school can learn how to read histograms, and at high school, and I think that's incredibly powerful. I think it's our job as educators to teach, the next generation about ECDFs. But I think, that type of openness there.
So histograms are intuitive because we can naturally visually associate height with some, or distances are like one of the primary modes with which we can relate quantitative information. So height is very useful, right? With an ECDF or the CDF, you don't get the height thing. You have to do the derivative thing in order to get to the height thing. So for communicating what is the most probable value, histograms are good if you binned it right. But if you didn't bin it right, you're gonna mislead your audience, right? So as a result, the only place where we saw an exception to that rule was the discrete probability distribution, where, yes, the height literally is just readable from the x-axis. With a continuous distribution, however, so one thing that we humans need to get around is with a continuous probability distribution, we like to talk about the most likely value, as if there is a probability associated with a single number with infinite number of decimal points. That doesn't exist, technically speaking, if I remember my probability correctly, does not exist, technically speaking, for a continuous probability distribution because there's no density under the curve at a point.
The probability of getting any particular value in a continuous distribution is zero.
Zero.
Yeah, you want the integral or the space underneath,
Exactly.
or the bin size.
Exactly. And that is the thing that we humans need to get around to finally understanding, right? As a race, as a human as a species, right? We need to understand that. If we don't get that, then we're stuck with histograms. Then we're stuck with histograms saying there's lots of probability associated with a range that my bar sort of covers. But that's still not, it still can be very easily abused. Whereas with CDFs, who let the dog out? With CDFs, you can never get away with binning biases. You have to use all the data. You have to honestly show all the data.
I love that you're framing this as human cognitive statistical evolution, to the next stage of our society together. And I think that's a great note on which to take a break as well. So why don't we take 15 minutes? I would urge, encourage you to not look at screens for the next 15 minutes. But seriously, because if you look at screens for the next 15 minutes, you'll have less capability to take in all the great information that we hope to share with you. So, and enjoy your snacks.
have a requirements.txt file. We'll recognize it and create a virtual letter. If you have a Docker file, you can create a Docker image and just stack that Docker image on top of it. So find your way.
And final question, I'm planning a big training program, so do you know if it's possible to kind of, if you have students completing notebooks by illustration, would it be possible to monitor what they are doing? Because we have online sessions and stuff, so it would be nice to see. If
That
these are
requires a
happening.
specialized platform.
Okay.
I'm afraid
Yeah,
Docker doesn't.
like that. That's what I thought.
The materials will always be up there, and if you have a GitHub account, you can fork it anytime. Where it's up.
Oh, the other thing I'd like to mention is these materials are a living document and work in progress. There's an issue tracker on GitHub, of course. Suggestions, critiques, anything else, very, very welcome. If you raise an issue that seems like it's a lot of work, I might request a pull request. But, you know, see what happens. Start it. Get going in 2 minutes. All right, everyone, time to get back into it. So the following section is on joint probability and conditional probability, which will play a large role in Bayesian inference and statistical thinking in this sense. There's a lot of hands-on exercises and coding in this section, and I've made an executive decision with Eric to not go through this. We'll leave that for the avid attendee after the fact. And the reason I'd like to do that is so that we can really start getting into the Bayes stuff. And I think the trade-off was spending a bit more time on the probability distribution and their stories. But I'm actually really happy we did that. Okay, so let's just think about joint probability. We've actually already encountered joint probabilities before, perhaps without knowing it. So P of A, comma B, is the probability that two events, A and B, both occur. So one example is getting two heads in a row, and we've already experienced that type of probability with the binomial distribution, right? Now, if A and B are independent, then the joint probability is just equal to the product of the two probabilities. But be warned, this is not always or even often the case that two things. If you're trying to do some research, like a lot of the time things are not going to be independent. Okay, so you need to be careful. This is, in high school or junior high or whatever it's called here. One way to think of this is considering AND as multiplication. So the probability of A and B is the probability of A multiplied by the probability of B. So then we've got a hands-on here, which you can do after the fact. Solutions are in the instructor notebook as well, verifying in the two fair coin flip case that P of A, B is equal to P of A times P of B, okay? And yeah, there are a few notes there which you can go through. Essentially, once again, this difference between probability and proportion, and using proportion as a proxy in simulation for probability, okay? Then there was a hands-on thinking about joint probability for birds. We've seen these birds before from the Galapagos, and the probability that two randomly selected birds have beak depths over 10. You can go through all of this yourself once again. And then we go on to think about conditional probability. Now, one way I'd like us to think about this, we can just have an example, right? I told you there were two types of birds in this data set. They're species Fortis and Scandens, right? So we've already answer the question, what's the probability or proportion of a finch beak having depth or length actually greater than 10? Now, we ask that for the general population. We can also ask it, conditioning it on the Fortis species and condition it on the Scandens. And the way, let's see, have I actually written that anywhere? Yeah, exactly. So we use this notation, P of A given B. So this would be the probability of beak length greater than 10 given that the species is Fortis or given that the species is Scandens. And the instructions instruct you how to go through these types of questions here, okay? Now, in fact, what we see is that these proportions are definitely different. We can't say much more, but we'll soon see how to use Bayesian hypothesis testing to see what else we can say about the differences between the species of finches.
And one thing to note, this is an epiphany that came to myself only like 6 months to a year ago, which is when we talk about like a data set where we have a probability, where we have a distribution of values that occur inside our data frame under one column, a conditional or two columns, like in the bird data set, conditional probability is just nothing more than filtering out a set of rows and then querying what is the probability of this value of interest that we have on another column. That is really all that conditional probability is if you need a concrete example.
So thank you for that, Eric. And that's actually really important because once again, that provides a computational protocol for thinking about abstract probabilistic structures, which I think is essentially what we're trying to do here and have been trying to do for a long time, and we'll go to the grave trying to do this. Didn't mean to get so morbid, but so there's actually a figure that I included in the notebook. It's a figure Eric produced, but I didn't include it in the repo accidentally. So this is just a nice way to, hey, it's not coming over, just a sec. Bear with me because it's nice. Why isn't? Exit full screen first. Oh yeah, that's it. Yep. Okay. So if we have the probability of X and the probability of Y, we can think about the joint distribution as living in this kind of space, right? Where we see a region of quite high density there, and it gets more and more spread out. And if we want to think about conditional distributions, if you want to condition on some value of Y here, we see a distribution of X there. Is there anything else you'd like to say about that? Okay, great. So I've got a kernel issue. Is that right? I think restarting the kernel's fine, isn't it? Lucky that I'm not using anything. Okay, just going to refresh. Okay. Yep, I'm going to restart. Yeah.
And for those of you who might have left the kernel idle for a little too long, I mean, that's how Binder, a free service on AWS, controls its costs, right? So like if you're not, you might have to refresh your browsers as well.
It's a free service and it's open source as well. It's an incredible project. Okay, so we'll go back to... I've lost more before. But the great thing is, this is actually the great thing. For the last thing we need to do in this notebook, I don't need anything. Yeah, and that's a great position to be in, right? That's absolute freedom right there. So, conditional and joint probabilities are related by the following. Okay, the probability of A times B is the probability of B and the probability of A, given that B is already satisfied, right? So it's P of A given B multiplied by the probability of B. And a homework exercise for the avid learner, that would be all of you. You can verify this using simulation resampling techniques that we've already used, right? So that's pretty cool. The one thing I'll say is that if A and B are independent, then the probability of A given B is just the probability of A. It doesn't rely on B at all, right? And then we get out that the probability of A and B is the probability of A times the probability of B, okay? So we're going to take 10 minutes now to do a hands-on exercise on drug testing, okay? So suppose that a test for using a particular drug is 99% sensitive and 99% specific. I'll tell you what that means. That means that the test will produce 99% true positive results for drug users and 99% true negative results for non-drug users. Now suppose that 0.5%, 5 in 1,000 of people are users. Now, let's say we randomly select an individual who tests positively. What I want you to do is use simulation, right, to figure out what's the probability that this person is actually a drug user, okay? So now if we can answer this, this is going to be really cool because it shows how we can move from knowing the probability of positivity being a user to the probability of being a user given positivity. And this is an MVP. I've clearly been working in a startup for too long, for being able to move from the probability of given data, probability of the data given a model to the probability of the model given the data. So in the spirit of this workshop, I sound like a cult leader here. It's now time to harness your computational power and the intuition of simulation to solve this drug testing example. Okay, so before doing so, I'm just wondering, what do you think the answer to the question is? What is the probability that a randomly selected individual with a positive drug test is a drug user? You don't answer it out loud, but I'd like you to write it down, okay? You know, either on a piece of paper or in your notebook. And
Just do not use your stickies, because we have purposes for the
we want you
stickies
to,
at the
we've got
end.
some stuff you need to write on your stickies afterwards. So essentially, what I want you to do is to take 10,000 subjects and then sample for the number of users. So you'll, you know there's a certain proportion of users, so sample for that. Not discreetly, don't be like it's 99%, but sample for it. Then the non-users will be the total number minus the users, and then sample once again from the users who tested positive, how many use and how many don't, and so forth. So all stickers down and then stickies up when you need to. And we'll take 10 minutes for this. Yeah, the question should be in your notebook as well, right? Yep. You're welcome. I'm just going to jump in and start writing stuff in the first cell, just because I'm so excited. Would you put up your hand if you've figured out the first cell? Cool. Yeah, we got a bunch of people. So we've got 10,000 subjects, and I want to sample for the number of users, okay? And if we know 5 in 1,000 will be users, I'm gonna, so once again, the story is a binomial story here, right? So we're gonna have np.random.binomial. Something, okay. Binomial, and we've got n people, and it's 5 in 1,000, so it's 0.005. And I just want to do it once, right? And then the number of non-users is just going to be, it's going to be n minus the number of users. Oh yeah, no, I need to, so I said I needed nothing. I said I had total freedom, but that's not true at all. Yeah, so the only thing I need is this first cell, but that is another option. I think all I need is NumPy, so. Okay. Right, so I'm just going to check how many users. Okay, so out of 100,000, well, I took 100,000 even though I wrote 10,000 here. Out of 100,000 users, there are 485 users, okay? So that's the first step. We've got some green stickies, but I'll take a couple more minutes. Are there any questions about that, or does that make sense? Okay, cool. We'll do the next bit in a couple of minutes. I did 100,000.
Oh, okay.
Yep, but you'd get something. Okay, so what I'm going to do is start working in the next cell now, okay? So we have a population of users. We have 485 users, right? So how many of these actually tested positive? So remember what I told you was that it's 99% sensitive, okay? So what type of story does that tell us? Yeah, and in terms of the probabilistic stories we've been talking about, what type of story is that? For each user, we have a certain probability. What's that? So you can think of it as like a coin flip, right? For each user, we have a 99% probability that something has happened, that they test positive. And so that precisely matches the story of the binomial distribution, okay? So once again, we can do, and I understand this is like, it was for me anyway when I first started thinking like this, quite a cognitive leap in terms of thinking about these data generative stories. What's up, man?
So just wondering here, you said before that a Poisson distribution was essentially the high sample size, low incidence probability limit of the binomial distribution. Does that sound right? Is this kind of exactly like that? Because testing positive is really rare. and we took a lot of samples. So could we just as easily here use Poisson instead of binomial? Or should we?
Yeah, please do.
If you have data that there is actually a probability, then regardless, like, yes, you could, but it would just be an approximation. So in the case where you actually have exact data, you might as well use it. And that's in the spirit of Bayesianism.
So you get a more precise result doing this, absolutely. The amount of people, the n, is the number of users, and then the probability of them testing positive is 0.9. Now, remember that 99% true negative results for non-drug users, okay? So non-positive, once again, this story is binomial. Each of them has this probability, right? So we're going to once again use binomial here, and we have non-users. Now, 99% of them will test negative, but we want to know how many of them will test positive, right? So it's going to be 0.01, okay? So I'm going to execute that cell now. Now, how many of those positive tests were for actual users? So I want, the number of positive users divided by the number of positive users plus the number of positive non-users, okay? Wow. Okay, so we see around 33%. That's a number of, okay. So out of all the positive tests, only 33% were for users, okay? Which intuitively, at least a first approximate statistical intuition, is quite mind-boggling, right? Because it was a 99% sensitive test. It will produce 99% true positive weights for drug users. First, did a lot of people, when they wrote it down, get something like that? Could you put up your hand if you got around between 30 and 40%? Okay. Put up your hand if you got over 50%. No shame here. Good. Put up your hand if you got under 10%. Okay. Where's the paradox? If we have something that's 99% true positive results, why do we get so few?
Yeah. So there are very few actual drug users. I guessed about 33%, and that was because if you take a sample of 1,000, right, 5 of those are going to be actual drug users. We'll say it's 100%, right, so you get all 5 of those positive, right, but there's still nearly 1,000 non-drug users, and you take 1% of those, there's 10, right, so there's 15 total that are flagged, 10 of them were non-users, 5 were actual users, so it's about 33%.
Beautiful, Nicholas. Thank you for that. And so what Nicholas has just done in language is a deterministic version of what we did via simulation just then. So he saw there were 5, and then there were 10. 5 is, add them together. That's going to be a third then. The really important point, of course, is that there are so few actual drug users, right? And this is what's known as the base rate fallacy. When people think about this generally, like non-quantitative people, they'll forget that there are so few, so they'll assume it's 90% or 99%, that type of stuff. Anybody who hasn't read Thinking Fast and Slow or some of Kahneman and Tversky's papers, there's a lot of great stuff with respect to these types of fallacies and cognitive biases in those papers and in that book. But why do we care? And as I stated before, the reason we care is that we've just moved from the probability of having a positive test, being a user, to the probability of being a user having a positive test, right? And these are the questions, as I said before, that science really asks. We're good at getting the probability of data given a model, but we're not great at giving the probability of a model given the data, okay? And what we've essentially done is computationally used a version of Bayes' theorem to do this. And Bayes' theorem states, I'm not even going to state it yet. I'm just going to, okay, I'll state it. It states that the probability of B given A is the probability of A given B times the probability of B divided by the probability of A. There's a lot of controversy over whether it should even be called a theorem or not. Can I have a mic, Eric? Just because I want to... The reason it's controversial is because... Okay, so I went to grad school in pure math, and it took me like 4 years to write 2 theorems. And I'm about to demonstrate Bayes' theorem in 10 seconds. So that's why it's controversial among mathematicians anyway. But it's illustrative, so knowing me, I'll probably get it wrong as well. But, so what did we say before? The probability of A times the probability of B is the probability of A given B times the probability of B, right? Okay, can everyone see this? Put up your hand if you can't. Damn, that was a small enough proportion for me to be slightly sorry. Okay, but due to symmetry, so the probability of B and A is equal to this, right? Like these two are the same. This is, yeah. I hope my grad school advisor doesn't see me start writing equalities in circles. Is the probability of B given A times the probability of B. So these two are equal. This is the wackiest commutative diagram I've ever drawn. So if we look at this equality here, then the probability of B given A is equal to, I'm going to divide both sides by P of A. So the probability of A given B times the probability of B over the probability of A. So I'm just going to hold that up. So, okay, that's the trophy. And that's Bayes' theorem, or Bayes' rule, or Bayes' law, or whatever you want to call it. And the great thing is, if what we have is the probability of a model, probability of data given a model, something like this, we can then convert into the probability of the model in the universe of the models given the data. And that's what we're going to do now. We've made it, Eric. It's great. Mathematicians spend years of their lives trying to prove theorems. So it's, calling something that elementary a theorem is, I think, it destroys the egos of many powerful people. Yeah, is it a lemma or a corollary or, there are lots of terms for, there is a better answer to that. I can't do it though. It would give too much away. I'm also very jealous of your ice cream sandwich. I feel like if I could do the rest of this tutorial eating an ice cream sandwich, that'd be a game changer. Okay, so oh yeah, I actually did this, great. Bayes' theorem can be used to analytically derive the solution to the drug testing example above. And we actually go through it. We won't do it now, but you've got the probability of user given positive, so on, yada, 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 0.32. Okay, great. So before we move on to doing concrete Bayesian inference now, are there any questions? Afterwards, yeah. But we've got an hour left, and we'll lose, yeah.
So one question here about what you just stated about moving between the probability of the data given the model and the model given the data. Just by looking at the equation, one of the pieces that you're going to need is the probability of the model. What is that thing, and how are we going to come up with that?
This being the probability of the model? Mm-hmm. Great question. And the answer is also great. The challenge here, okay, so when we look at this formulation, this essentially is the probability of the data given the model, or the likelihood of the data given the model, okay? So that's what we call the likelihood. This is the probability of the model before we see any data, right? Prior to seeing the data, actually. For that reason, this is called the prior, which is one of the most controversial aspects of Bayesian inference. This is the posterior because it's after seeing the data. So essentially your question boils down to, how do we choose a prior, right? We'll get there. And a cheating answer to that is get enough data and your prior doesn't matter, right? Andrew Gelman once said to me, he was like, I said to him, how do you explain Bayesian inference? And he was like, you've got data and a prior, and if you have a lot of data, your prior doesn't matter. And if you don't have a lot of data, your prior matters, that's it. And I was like, dude, you wrote like a 700-page book about this. He's like, yeah, but that's pretty much it. Okay, fantastic. So notebook 2, this is where it gets. You thought that was exciting. I thought that was exciting. Okay, so let's open notebook 2 and import. I'll just talk you through what we're importing. You know, we've got our NumPy, our Pandas, Seaborn, Matplotlib for visualization. PyMC3 will be our probabilistic programming stuff. IPy widgets to just have a bit of interactive fun. RViz is for data visualization for probabilistic programming outputs, and then the Matplotlib inline we discussed before, and SNS.set. So, PyMC3 is the package we use for probabilistic programming to do Bayesian inference at a high level, essentially, where it abstracts over a lot of the ideas of figuring out the internals of distributions and that type of stuff, where the distributions themselves are first-class citizens. Okay, so learning objectives. Understand what priors, likelihoods, and posteriors are. We've got a sense of that. Use random sampling for parameter estimation to appreciate the relationship between sample size, posterior distribution, along with the effects of the prior. And hopefully we get to using probabilistic programming for parameter estimation and use probabilistic programming for hypothesis testing. I'm going to get rid of that toolbar. Okay, so once again, I want to say we flipped a bias coin several times, our binomial distribution. We want to estimate the probability of heads from the number of heads we saw. Statistical intuition tells us our best estimate is the number of heads divided by the total number of flibs. However, it doesn't tell us how certain we can be of this estimate, and this type of intuition doesn't extend to even slightly more complex examples. So Bayesian inference helps us here. We can calculate the probability of a particular P given data D by setting the A in Bayes' theorem equal to P and B equal to D. So that's a mouthful, but setting A, wait a sec, yeah, A equal to P and B equal to D, we get the probability of a particular P, right, of whatever the probability of the coin flip is, given the data, is equal to the probability of the data given a P, we know how to calculate that, times this prior term, the probability of P, divided by the probability of the data, okay? Now, in this equation, we call, and I've just been through this, but it's worth reiterating, we call P of P the prior distribution, P of D given P the likelihood, and P of P given D the posterior distribution, okay? The intuition is the prior is the distribution that contains our knowledge about P prior to the introduction of the data. The posterior is the distribution containing our knowledge about P after considering the data. I also want to mention that I've just used the term probability in 3 different ways. I've overloaded it completely, and that's a big challenge in the field and in the literature. I've referred to the probability P of seeing a head when flipping a coin, the resulting binomial probability distribution P of D given P, of seeing the data given P, and then the prior and posterior probability distributions of P, including our uncertainty about the value of P. So if at any point I say the probability and you don't know which one I'm talking about, please just like throw a tomato at my head or something. Okay. Yeah, I'll catch it in my mouth. Okay. The other thing that's very important is that we really only need to know the posterior up to multiplication by a constant, okay? This is because we only really care about the values of p of the posterior relative to each other. For example, what is the most likely value of p, okay, of the probability of getting a heads? So we only need to know what the posterior is proportional as a proportion. So we don't actually need to worry about the denominator, which doesn't rely on p, okay? So essentially, we're interested in this term, the probability of the data, so the likelihood times the prior. So we're going to get coding soon, but before that, a word about the prior, okay? What is the prior? The prior is what do we know about p before we see any data, okay? So in the coin flip case, or in the binomial case, or in the Bernoulli trial case, what do we know about p? Can it be 10? No. It's between 0 and 1, okay? We know, so that's some prior information we have, okay? That's between 0 and 1. If we haven't flipped any coins yet, we don't know much else. So it seems logical that all values of p within this interval are equally likely. So we could, as a prior, just set the uniform distribution, okay? We can also try some other different priors and see how they change the result we get for the posterior. There are other, okay, it's known as an uninformative prior because it contains little information. We'll talk about other uninformative priors soon. People who like to hate on Bayesian inference, I like that I wrote like to hate, I forgot I wrote that. Haters gonna hate, right, Eric? Tend to claim that the need to choose a prior makes Bayesian methods somewhat arbitrary. But once again, if you have enough data, the likelihood dominates over the prior. The latter doesn't matter so much. Also, you're once again making your assumptions clear and explicit. You can say, this is the prior I use, and if someone feels another prior should be used, you can see what the result is given that, which doesn't occur as much as it would need to in other forms of statistics. Essential remark. We get the whole distribution of what this coin flip probability can look like, not merely a point estimate plus error bars. We get the entire distribution, as we'll see. So I think all that having been said, let's get to work. We've got until 4:40, is that right? Okay, whew, got our work cut out for us. Okay, so we're going to generate some coin flips and try to estimate the probability of getting heads, okay? So 2 notes, we're going to get a bit mathematical now, but not very. Given data D consisting of n coin tosses and k heads, the likelihood function is given by, so L or P of data given P is P to the power, this is actually incorrect, is P to the power of, proportional to P to the power of k times 1 minus P to the power of n minus k. It's proportional to because you've got this binomial factor up front, right? Like remember n choose k from high school? That's what you'll see there. And given a uniform prior, the posterior is proportional to the likelihood. So what we're going to do now is we're going to define a function called plot posterior, and we're going to plot the posterior given some data. But then what we're going to do is we're going to use the IPython interact widget to build another plot where we can have sliders with number of data points and probability to see how it changes. Okay, so let me, just 1 second. So I'll get you to start setting the seed. Feel free to... Okay. So we're going to do np.random.seed. I'm going to set it seed equal to 42. So remember the function is taking in the probability p, and I've got some defaults. And I've got doc strings, always write doc strings. So probability p and size of data n, and so it's going to be random. Once again, we're flipping a coin, so it's our binomial story, n, p. Now, the x-axis for the PDF, it's going to go from 0 to 1, so I'll just, there are a number of ways to do this, but I'll use linspace. From 0 to 1, maybe 100 points. The prior is equal to 1, because it's uniform. The posterior, so I've written I really should call it the likelihood. I should call it the likelihood, but because the prior is 1, the likelihood and the posterior are the same. So I'm going to cheat slightly for this. So it's going to be x, the x value to the n, which is number of successes, which is that k here, times 1 minus x to the number of failures. So total n minus n successes. Oh, no, that's right. I'm going to multiply it by the prior here. Okay? So that is actually the posterior, which is good. Then I'm just going to normalize it. I'm going to divide the posterior by the maximum.
Your x to the power of little n or x to the power of big N? I just want to make sure.
Yeah, it's actually, it's x to the power of n successes. Yes, exactly. Perfect. Thank you very much. Okay. Also, like, I'm setting a seed in a function definition. Like, that's really bad. So, but never do that except now. It's not really bad. Life could be worse. Okay, so I'm going to execute that. Now, I'm going to plot the posterior for 10 coin flips. Okay? So, to do that, all I need to do is call plot posterior. And we've got a default for p, so I'm just going to choose n equal to 10. Hey, look at that. That's a posterior. So we see that, there's a peak around 0.7, and p was 0.6. So remember, we're generating our posterior. So it looks like, a credible region occurs within here, right? For the value for p, and we only have n data points. So firstly, are there any questions about that? So you've just plotted your first posterior in this tutorial as well, which is pretty cool. Now it's really going to get exciting, and we're going to use the interact widget, which allows us to have a little slider or a couple of sliders. So we're going to have the plot posterior plot. And we want to have sliders that can move p, which is the probability of getting heads, right? And the probability, remember, goes from 0 to 1, and I'm going to allow increments of 0.01. Oh, yeah. Of course. And then n, I'm going to allow to go from, let's just say 1 to 1,000 with increments of 1, okay?
This is why we pair code.
Yeah, exactly. Uh-oh.
You forgot to put those parentheses on P.
I sure did. This is why we pair code. I want to actually start with 0 data points. Because if you start with 0 data points, you just get the prior, right? If you have no data, your likelihood does nothing, and the posterior is just the prior, okay? So we have uniform, right? So remember, this is the posterior for P, the probability of getting heads. Okay. Now, what happens if I start to flip coins? I'm going to flip it once. Whoa, okay. So it looks like now I must have flipped a head, okay, because the posterior is a lot more weighted up there, okay? Now I'm going to flip again, okay? Flip to tail. I'm going to keep flipping. And as you see, as I keep flipping coins, so I'm pressing the right arrow after clicking on this, I can also drag that, you can see that the posterior gets narrower and narrower and narrower. right? And you can see it's getting very close to 0.6. So as we generate more and more data, we get closer and closer to our actual value. On top of that, we get the whole, this is taking a while. That'll take a bit of time. But on top of that, you'll see we actually get the whole distribution of possible values of P. So as we'll see when we look at PyMC3, and you could hand code this, you can calculate and tell someone what is, in your posterior, what's the probability of seeing a value less than or equal to 0.6, okay? So if we're looking at click-through rates and you need to report to your product manager or whoever runs the growth team the probability that this click-through rate is less than 0.4, something along those lines, you can read that off this, whereas in the previous way of doing this, you don't have the entire distribution. So now you have this, which is very cool. And these things are, in our notes for discussion as well. So as you generate more and more data, your posterior gets narrower. You get more and more certain of your estimate, okay? The other thing that you can play around with, this P slider. That's a horrible term. You need more data to be certain of your estimate when P is equal to 0.5 as opposed to when it's 0 or 1. If you just think about that intuitively. If you're always going to get ahead, if you're always going to get heads, if P is equal to 1, you flip it 5, 6, 7 times and you've got 7 heads, you can be pretty sure that it's close to 1, right? Whereas if you're getting heads, tails, heads, tails, heads, tails, you still can't be quite certain. You can see that distribution, see the way that that's affected in the distribution. So having said all that, I'd like to talk about the choice of priors. Before going on to that, are there any questions?
Hold on, please. We want to record it, so me first.
Oh, okay, me first. Okay. If you scroll back up to the sliders, I'm noticing if you increment and start n at 0 and increment by 1, I'm wondering if the pattern I'm seeing is a result of like just a formulation or the programming or the RNG. So if you keep increment by 1 with the arrows, you'll see a weird behavior to it. It'll like jolt back and forth.
It's as you...
Is it like that? Where it jolts back, is that something with the RNG? Does that have to do with...
No, it's just because you've got a small amount of data, so each new data point changes the posterior quite a bit. Yeah. Just as you see, if you go from 0 to 1, it's going to do that. Yeah. You have a question up there?
Yes. Again, I may have blanked at some point. Regarding the prior in the context of the experiment of flipping a coin in human language, what is again the prior in that experiment?
Could you say that again?
In the experiment of flipping the coin, can you say in human language what is the prior and why did you choose one?
Yeah, so the prior is before you collect any data, it contains everything you know about what the probability of getting heads is.
And you chose one because you know you're going to get one side of the other or the other of the coin?
No. So the reason I chose, I didn't choose one per se, I chose the uniform distribution where anything is equally possible, right? So the probability of heads being 0.2 is as likely as it being 0.4, is as likely as it being 0.5.
So when Hugo chose the integer 1, it is because he is saying that on the interval from 0 to 1, the probability distribution takes on the value of 1 at all points under the height of that distribution in the interval 0, 1 is 1. Now, if we were doing something wrong and modeling a probability value with a prior distribution that can take on a value from 0 to 2, which is completely wrong. You cannot have a probability value that is beyond 1. he would have put 0.5 there. Because the uniform distribution on the interval 0, 2, the area underneath it must sum to 1. So the height is there. So that's where that 1 comes from. That's where the 1 in the function as the prior comes from. It is coming from the fact that there is a unit interval, 0, 1, and that's all the probability that we're willing to consider. And so the height, the area under that line must equal to 1, and so therefore it's 1 everywhere. Okay?
Thank you. Very good question.
Okay, so Hugo, can you put up like the n equals 0 case? Notice how in every probability distribution, any probability distribution, the area under the line must sum to 1. So if we scrolled over and made n equals 3, can we do that? All right, okay, cool, even that. In this probability distribution, the total area underneath here also sums to 1.
So it actually isn't, because I've normalized with respect to the peak, not to...
Sure.
So in this case, but...
Sure, but
for any
yes,
probability...
for any true probability distribution, not the one that Hugo's showing. But, sorry. So the 1 in the function that Hugo wrote up there expresses the idea that when having seen no data on just the unit interval from 0 to 1.0 on the x-axis, we need to choose a number at the y-axis such that a single horizontal line across gives us the value of 1 for the area underneath that line. All right? And so that's where the 1 comes from. Counterfactually, if we had the interval 0 to 2, in order for the area under that horizontal line to be equal to 1, we would have chosen 0.5, right? So that's where the 1.0 comes from. I think that's going to hinder progress.
What was the question?
Can we change NC from 0 to 2? And that will hinder progress for today. We can always talk about later.
Yeah, we can do it afterwards as well. Okay, so essentially this was to demonstrate that as you collect more data, your distribution gets more and more narrow, okay? And you can play around with that. I'll say a few words about the choice of the prior. I won't spend as much time on this as I'd like, but I'll share some resources. There are informative priors which express specific, definite information. For example, if you got a coin from the mint, we may use an informative prior with a peak at p 0.05 and small variance because you would expect it to be a fair coin. Whereas if you got a coin from a crazy casino, I hate that example, but you could imagine that it's peaked at both ends and it's very unlikely that the probability is 0.5. Weakly informative priors express partial information about a variable, such as a peak at 0.5 with a larger variance. And uninformative express no information about a variable except what we know for sure, such as knowing constraints on what it can actually be. Now I want to say something about the uniform distribution. You may think it's uninformative, okay? However, what if I've been thinking about this question in terms of the probability P, and what if Eric is thinking about, Eric's a contrarian, so what if he's thinking about this in terms of the odds ratio, which is R, which is P over 1 minus P, okay? If he's thinking about the odds ratio, Eric rightly feels that he has no prior knowledge as to what R is, and thus chooses the uniform prior on R. I've chosen the uniform prior on P, and you can do a transformation of variables and show that these two are not actually, the uniform prior on P when transformed to R is not the uniform prior on R. So in that sense, it's not quite uninformative. But there are priors that are invariant under these types of transformations, one of which is called the Jeffreys prior. And I'm just gonna, the Jeffreys prior is defined in an information theoretic way, but in the binomial coin flip case, the Jeffreys prior is given by 1 over the square root of P times 1 minus P. And what I'm going to do now is copy and paste from the instructor notebook. I was going to get you to write this code, but I really want to move on to the probabilistic programming stuff. What I'm going to do, and feel free to do the same now or afterwards as well, but I'm going to paste. It's a similar plotting function as above, but it plots the Jeffreys prior and it plots the posteriors given the Jeffreys prior and the uniform prior. So I'm going to do that, and then I'm going to create this interactive plot. And then we'll wrap up with half an hour of probabilistic programming. Should be very fun. Okay, so now I'm going to create this interactive plot. I'd urge you, copy and paste it at will, but maybe just have a look at this now. The uniform prior is, as we saw, uniform between 0 and 1 on 1. The Jeffreys prior is pretty crazy here. It's very different. But what I want to show you, right, and this is the point, is that as we increase n, the uniform, I mean, even after 22 coin flips, they're getting pretty close, okay? So this is an argument for thinking about your scientific question, how much data you need to collect with respect to being, more confident in your posterior estimate. There are a lot of resources on choosing priors. I don't think it's, in the end, as scary as it seems, but there is a barrier to entry, and this was kind of just a small introduction into the wonderful world of priors. I wouldn't, I'll share some links to the Stan's and other probabilistic programming language. They have a lot of information on priors, but they get pretty heated. It's what last year I referred to as the prior wars, right? They, you don't want to get involved in that too much. So the question here I've already answered. What happens to the posteriors as you generate more and more data? Okay, so we've got half an hour left. And so I'd love to introduce you to the world of probabilistic programming in this final time. Okay, and look, well done. You've learned the basics of Bayesian model building. Now, what are the steps? The steps are to completely specify the model in terms of probability distributions. What does this include? This includes specifying what the form of the sampling distribution of the data is. Is it binomial, Poisson, Gaussian? And what form describes our uncertainty in the unknown parameters. So this is the prior information, okay? So this formulation I adapted from Chris Fonsbeck's workshop. Check out his resources as well. He said it so well there. And then what you do is, in the most basic sense, you calculate the posterior distribution. After that, and we won't get to this, but some of the notebooks, there's a plethora of notebooks. This is notebook 2. There are like 7 notebooks in this repository. And Erica's made some great ones on computing posterior predictive checks. And what that does is it takes your posterior distribution and plots it against the data that you actually have, or generates the data given your posterior, plots it against the data, and you can see how well it corresponds in terms of validating your model, right? But for the course of, for the purposes of now, we're going to specify the form of the sampling distribution, specify our uncertainty of the unknown parameters, and calculate the posterior, okay? In the above, as I said, the form of the sampling distribution was binomial, described by the likelihood, and the uncertainty around the unknown parameter p captured the prior, was captured by the prior. I keep saying things before they're here. I mean, this is why I wrote this, I suppose. But there is also a third step that Eric will cover, which is performing posterior predictive checks. And at a high level, it's making sure your model actually makes sense. Okay, so now we're going to use PyMC3. There's loads about PyMC3. I meant to write there's loads of cool stuff about PyMC3 and the paradigm, 2 of which are, as I've mentioned probably ad nauseum so far, probability distributions are first-class citizens here, in that we can assign the distributions to variables and use them intuitively to mirror how we think about priors, likelihoods, and posteriors, okay? The other cool thing is that PyMC3 calculates the posterior for us. For those interested, using Markov chain Monte Carlo or variational inference, we'll use the no U-turn sampler today, which is a special case of MCMC, if I recall correctly. So we're going to just do another MVP case of click-through rate, which is a binomial coin flip again. Remember, we're talking about whether people click or not. Each person has a certain probability of clicking. That story, once again, matches our binomial distribution story, so we can use that. And let's see. Yeah, then we may go on to comparing click-through rates, giving a product change. So this would be a Bayesian formulation of an A/B test if we want to do that. But without further ado, I'm going to generate the click-through data to begin with. So the probability of clicking through is 0.15. The number of people we have coming through is 150. And the number of successes is going to be NP. Remember, I'm summing again. And is this what I want to do? Yep. NP dot random binomial. I don't think I need the sum there, right? N P A, and I'm just going to print this out. Yep. Okay, great. So we've got the number of successes in this experiment, okay? And that's just generating our data. So, but remember, you're going to be out there collecting this data and then trying to, we don't know what PA is. We know what capital N is because they're the number of data points we've collected, but we don't know what P of A is. But we've set that to see what happens next and if it coincides with this. So now it's time to build the probability model. This is so much fun. Noticing that our model has a constant click-through rate resulting in click or not is a biased coin flip. The sampling distribution, what's that story? It's a binomial again, and we need to encode this in the likelihood. Now there's a single parameter. We know how many data points we get, capital N. There's a single parameter that we have some uncertainty around, P. We need to describe that uncertainty using a prior. And we're going to use a uniform prior. You can use what you want, whenever you want. But right now, we're going to use a uniform prior. Okay, so now there's a slight quirk to the API for PyMC3. And it uses, yeah, exactly. It uses with, which is a context manager. And we'll do that now. So I'm going to use the model constructor to build this model, and essentially whatever I do in this context manager now is building this model, which is called model, okay? So firstly, I want a prior, and remember I said the prior is going to be uniform, and so, this is so good. So PM dot, what do you think, so remember I imported PyMC3 as PM? If I'm going to do a uniform distribution, what do you think the next thing's going to be? Uniform. See, seriously, this is why I came to Cleveland. This and the Rock and Roll Hall of Fame, right? Okay, so uniform, and I want to specify the name of the variable in some sense. This is slightly quirky because essentially it's kind of common practice to call it prob, but I'm going to call it P for the time being just so I'm consistent downstream. Now the binomial likelihood, right? I've got to use a PyMC3 distribution, and once again, it's just going to be PM dot binomial. Okay? Now, for the likelihood, right? I need to specify what I want to call it, which is Y. I need to specify the number of data points. So remember the likelihood is this term P of A, B, which contains all the information about the data and your likelihood model and that type of stuff. So I need to put this N into it. That's the number of data points. Now I need to tell it something about the prior. It has this.
So when you specify N there, you're specifying the subset of the data that meets the condition.
No, I'm specifying the number of data points I've collected.
In total.
Yeah, exactly. And I'll scroll back up. It's kind of similar, well, it's actually analogous to, specifying this likelihood contains K and N minus K. And if you sum those together, that will give you the number of data points as well. So I need to specify that. Then I need to specify, remember in the likelihood, there's this P, the probability of getting ahead, and getting ahead, flipping ahead, and I'm getting confused because ahead is a single word and getting ahead is a term that means something else as well. But so I need to specify that I'm looking, the probability here, I'm actually looking at this prior. And on top of that, remember, you need to specify the actual data that you receive. So what I want to tell it is how many successes I actually got, right? So I've got the number, whoa. I wonder, okay. Number of successes, A. Okay, so what I've done here, I've specified the sampling distribution here, and I've specified the prior on P, just as, and I'm going to scroll back up. Sorry if you're copying my code. Just as here, I specified the likelihood here and the prior there, okay? But now, instead of hand coding all of these like variables and numbers and ints and that type of stuff, it's abstracted over all of that. All I need to do is express probability distributions, right? So that's essentially what I mean by saying probability distributions are the first-class citizens of probabilistic programming. Okay? So now I can execute this cell and it will build this model. Please, no errors.
This usually takes some time because there is a compilation step from Python syntax to Theano under the hood. I'm helping out a little bit with PyMC4, which is the next generation PyMC, and we'll be moving off to TensorFlow probability instead. There's a lot of work to be done. I'll be in Montreal to hack on the project with a bunch of others from the PyMC project at the end of May. But yes, we'll be keeping everybody updated on that. The goal, though, is to keep a nice API. We've seen the APIs from most other probabilistic programming languages. They're not beginner-friendly. They are very tailored towards researchers who know math already, right? So we're trying to keep this like a nice API for day-to-day work, and I use PyMC3 myself in my day-to-day work.
And is there any idea for a release date for PyMC4? No. Okay. Okay, so that model's been built, and I've mentioned what I think of the API for PyMC3. I think I want to go through this a bit more, and then we can open for discussion and any questions, because what I want to do now is to get PyMC3 really working for us to build this posterior, okay? So, once again, what we do is, with model, okay, we want to, I actually think I made it a big M. Yeah, yeah. And that's actually, yeah. Yeah, exactly. Generally, it's convention to do model with a small m, but we're just having such a great time, I thought, you know, to be exclamatory. Okay. So what do we do now? We want to generate samples of the posterior distribution, right? And so we're using PyMC3, and I mean, if you're trying to draw samples, it would make sense if the function was called sample. So that's, you know, that's good. And the thing is, the way this works, and maybe Eric can say a few more words about this, the posterior can be a crazy space, right? And what these algorithms do is they kind of move around it, trying to figure out what the distribution looks like. It'll jump around, make a few mistakes here and there, particularly at the start. So you want some sort of burn-in period, right? Which will be, is it 500 by default? So 500 steps moving around this posterior by default. But then you'll want enough points in order to get an idea of the distribution. A nice default is 2000, which we'll use, but maybe you can say a bit more.
Yeah, so for this example, I would encourage you not to be too worried about like weird posterior distributions and the likes, but Hugo mentioned it because for those of you who are a bit more, who may be a bit more inclined and or trained in have prior training, it is a thing that PyMC does really well in that PyMC uses a really cool sampler called no U-turn sampling, and that helps to avoid regions of posterior distributions that have weird shapes and are really, or rather, no, sorry, I'm blabbering at this point. Sorry, let me backtrack a little bit, okay? So for some more complicated models, you'll have extremely weirdly shaped posterior distributions. You can think of it as like the posterior distribution, imagine it looking like a donut. So you slice a donut in half, you've got this plane, and then there's this ridge where there's high probability density, and then it's like flat everywhere else, right? If you were to use a plain MCMC sampler, this is of course for those who know a bit more, you'll get stuck in like little parts of the posterior distribution, whereas with no U-turn sampling, you actually can very efficiently, in terms of number of samples required, go around this donut ring really quickly, right? You don't need like 1 million samples, you only need 2,000 or 3,000 or a few thousand. Now for those of you for whom that statement just went over your head, don't worry about it. Like, same defaults are set. In this particular case, yeah, you can trust your defaults.
That went over my head because I'm thinking about donuts now. Thank you. So what I'm actually going to do is we're going to generate the posterior and then plot it. But what I'm going to do is just plot it after the fact. Yeah. Okay. So this will take a bit of time. Don't worry about the end jobs is equal to 1 for the time being. This is. Yep.
Another word on what's going on over here. What's going on over here is analogous to throwing darts. That's a way of thinking about MCMC. So we have, if you think back to Hugo's posterior distributions, we're throwing 2,000 darts at the problem, and we're saying how many of those darts lie within the area under the curve of the unit 0, 1 region. That's all we're saying, right? We're throwing darts at the problem. That's what we mean by MCMC sampling. We're calculating the area under the curve. We're doing an integration. And that will help us compute what this posterior distribution looks like.
And now we're going to plot it. Okay, great. So what we see, let's just go back up to see the probability was actually 0.15, and I'm actually going to change this to a hist. Feel free to do that. Okay, so what we see here is that the mean of our posterior is 0.2, which, remember, we only had 150 data points, right? So 0.2 isn't too far from 0.15, but it isn't too close either. But if we look at the 94% highest posterior density, right, we can see that 0.15 is definitely contained in there, okay? And once again, we have the whole distribution. So if your product manager or whoever's in charge of your growth team came and said, actually, I really want to know, what the probability of the click-through rate being greater than 0.22 is, okay? You can actually, is it ref val is equal to 0.22. Okay, we're going to plot this again. Now, what you can see is that the probability of it being greater than 0.22 is 32.6. It being less than is 67.5. There are a lot of other parts of the API here which allow you to draw out information like this. But essentially, having the entire posterior distribution allows you to answer as many questions as possible. On top of that, once again, we've built in all the assumptions that relate to the stories that we think are generating the data as well. And I think that's probably the biggest takeaway I'd like you to take away. So there's an option now we've got 10 minutes. We can do one more example. I mean, these examples are so good. I mean, we wrote them, right? So, but perhaps if there's 10 minutes left, you all would prefer to just have a general discussion about what we've learned today and what we've discussed. If you'd like to do more coding, put up your hand. If you'd like to talk and chat. It's pretty even. Most people didn't put up their hands, so.
I think some people want to leave. We're not fun enough.
Yeah. Yeah, let's have some questions.
Do you have a video of this entire tutorial? Because obviously we couldn't go through the full thing today, but presumably you have.
We made an attempt at SciPy 2018 and promptly realized we need 2 of these sessions to go through everything. So if you want the compressed version, SciPy 2018 has all the YouTube videos up for the tutorials. We're trying to see whether we can do, we're looking for venues for the full tutorial. But so far, like, no venue has been able to accommodate 2 parts together. And I think partly it's my fault because I still help out with the network analysis one, so they don't want to burden the tutorial instructor with too many things. So next year I might ask Myrtle, my tutorial instructor co-instructor for network analysis, to take it all on his own, and then we can then have fun with Bayes, hopefully.
So I'll add to that, and we'll include in the repo. There is a video up, as Eric said, for our tutorial last year at SciPy. It has more of notebooks after this. Notebook 1 was very different. We didn't talk about storytelling and probability distribution. We did random number generation, but we didn't frame it in terms of this is how we can talk about data generating processes. On top of that, if further material is something people would like to see, I'd urge you to write to PyCon and SciPy to let them know that, you know, what you thought of this tutorial and that an extension maybe
yes,
fun as well.
and I will add there are lots of talks on PyMC3. There are lots of talks on PyMC3 that you will find over PyCon, Strata, PyData, etc. So those are definitely available. And by the way, if you want to go beyond just like single parameter estimation, which are the foundations, but still, you know, nonetheless kind of on the simpler side, and you want to go to more complex models, there's a lot of good tutorials on the PyMC docs. They have that. They have that there. There's one question back here.
Thanks a lot, Hugo. Have you thought about writing a book on this? Because I really like the language that you used, and I feel like it's a very approachable sort of means to a very technical topic. You know what I mean?
I appreciate that question and the compliment embedded in it. So I have thought about writing. Okay, for context, this is a colleague of mine and friend David who asked me to write a book every day. But I have thought about writing a book about it, but I don't know if a book is the best way to develop this material. Yeah, I wonder whether like videos with notebooks scrolling through. O'Reilly, I don't know if they still have it. Have you seen these O'Reilly Orioles? They're really cool. They have a video and a Jupyter notebook, and you can scroll through the video and code along and click on a cell, and it goes to that part of the video. So, in short, I have and would love to spend more time doing this type of stuff. And maybe you can intern with me, and we can. Yeah. Thanks, David.
I have a couple of questions about, I guess, convergence would be the right term. Earlier in the second half of the session, you mentioned that If you have little data, the prior matters a lot, and if you have a lot of data, the prior doesn't really matter. Is that always true? Is there a theorem that proves that it doesn't really matter what prior you choose if you have infinite data, or can you somehow get stuck in a local minimum and never predict the right posterior? That's the first question. And the second question was about the defaults that we just saw. That's the number of parameters that you're estimating. Are those defaults still valid even if you're estimating many parameters, or is that only for the one parameter case?
So I'll take the second one first. 2000 is a good sane default for the case where, for a wide variety of cases actually. So 2000 samples only says return to me 2000 draws from the estimated posterior, basically, through MCMC sampling. There's like rejection and acceptance probabilities and stuff, but only 2000 samples will be recorded. And 2000 just is like a good enough number that you can grok the shape of the probability distribution. And really that's all you're interested in. Most people, we just want to look at the shape of the probability distribution, make sure it's correct, and then have a bunch of formal sanity checks that we can do later. Now, long-range convergence.
I can answer it in a kind of a strange way. I can't reference the actual theorems, but I think the more data you have, the less the prior will matter. But depending on the priors, you may need more and more data. If you have
actually, there is one particular case where your prior can never be changed, and that is the equivalent of your extremely stubborn old uncle, right? That is when you set that there's no probability associated with any other value but 1 or 0 or some other fixed number. And if you do the math in a principled fashion, you like do the calculation, you're not going to change that prior's mind. And
because
so
it's multiplication, right?
Yes,
because you're multiplying a likelihood by a prior. If the prior says 0 for everything except something, you can't change that prior's mind.
That's right. So that is the one place where your prior will never get swamped by your data, because your prior assigns 0 probability to anything but that particular value.
Could you go to the last chart where you put the ref val on the histogram?
Absolutely.
I'm wondering, because people, I feel like p-values are the most misused thing in the world in terms of statements that folks make. Could you make the correct statement about the text in orange there? So what is that actually saying about the probability, and then the 0.22 is the reference number?
Yeah, I'm pretty sure the correct statement is the one I made before, because I didn't say p-value.
Oh no,
Yeah.
I didn't hear you make that statement.
Yeah. Okay. So the statement is that given the assumptions we've made, and the data, and the choice of prior, which is built into the assumptions, that there's a 32.6% chance of the click-through rate or whatever it is being greater than 0.22. Yep. Exactly.
And this is the nice thing about Bayesian inference compared to p-values. P-values are not the probability that your value is that value. It's not. Or it's not the probability that your hypothesis is correct either. The p-value is the probability of obtaining that result or something more extreme under a very specific null hypothesis. And that null hypothesis is sometimes implicit in most of the canned statistical procedures. You'll hear me rant about this at my talk.
I'll build on that by saying that there was a study, there may even be a video of it, of research scientists who've all used p-values in publications being asked what the definition of a p-value is. And you hear some crazy stuff.
Yes. On the other hand, in a Bayesian framework, it is plain English language, the probability that the value is greater than or less than this particular thing that we've thresholded at, that's exactly what it is. It is the probability that that value, the true value, is greater than this or less than that, et cetera, et cetera. That's all it is, plain English.
And I'll just state one other thing. The next example is parameter estimation for the mean of a population of the lengths of the finch beaks, I think. And you'll just see there that, all the conversations we had about data generating processes and stories allows you to, say a normal prior for mu for beak length with a mean and a particular standard deviation. And what happens after that is, I think at the very bottom, there's actually a Bayesian hypothesis testing of beak length differences between species, which uses all of this and provides a different formulation to this p-value with respect to effect size in particular. So I urge you all to go through that and ping us on the issue tracker with any questions, or if you do it, I mean, we're around all week as well, so yeah.
Back there.
So what is the standard strategy for dealing with like low probability success event, like in a bank default kind of a situation, like a person may default or
What was the example?
A fraud kind of a situation where there is like a low default, low success or low event rate kind of condition, like 1 in 100,000 or something. So what's the best way to deal in a Bayesian framework?
Get lots of data.
So in that particular scenario where you have like a million non-fraud and then like that one thing, that one example where the fraud event happens, you essentially have, and if you essentially have a 1 in a million estimator in your data. It's at that place where even if you had like a million other data points, the thing that's of interest belongs to the realm of small data. You have only one. So that means you need to borrow information and justify it from other fields and bake that into a prior. You need an informative prior in that scenario. You can't get away from that. So yeah, by the way, a lot of big data is not really big data. A lot of big data is just lots of small data put together. So don't believe the hype that like big data is gonna solve everything, because it's actually a lot of small data, and that's where Bayesian methods really come in really handy. You can look at small data in a very mathematically principled fashion and just put all your cards on the table, right? My assumptions are expressed as probability distributions. There's nothing I'm hiding. There's nothing I'm implicitly assuming. They're all there on the table. What do you not agree with? What do you not agree with? If you don't agree with something, give me a different probability distribution and justify it. We have to have that conversation. That's called doing science. That's the science of data science. Fighting words. I'm very frustrated, you can tell.
On that note, thank you all very much for joining us.